The derivative as a rate of change. Many applications in calculus depend on our ability to deduce facts about a function from information concerning its derivatives. Because f prime of x represents the slope of the curve y equals f of x at the point x, f of x, it tells us the direction in which the curve proceeds at each point. So it's reasonable to expect that information about f prime of x will provide us with information about f of x. In this section, we're going to go through and evaluate that. Let's do a quick review of some concepts from college algebra. The definition of increasing, decreasing, and local extrema. A function is increasing on an interval AB if the y values increase as the x values increase on that interval. So we can see here as our x values are increasing, and remember increasing is always going from left to right here for our x values, you can see our y values are increasing on this piece, and then again right here. So these would be the increasing intervals of this function. A function is decreasing on an open interval, AB, if the y values decrease as the x values increase on that interval. So again, we can see here as these x values are increasing, these y values are going down, they're decreasing. So I always one of the ways that I tell students to you can see if it's increasing or decreasing, if you write your name on it and your name is going up, it's increasing. And then if you write your name and it's going down, it's decreasing. You can also look at this turtle. We're going to use an applet with this turtle on the next slide, but here the turtle would be going up the mountain. And then the turtle would be sliding down the mountain. So that's another way to think about it. All right, local extrema. So a function has a local maximum at a point x equals c if nearby f of x is the largest y value. So let's talk about what that means. So if I always call it like a neighborhood. So if I drew a neighborhood right in here, I could say that's a local maximum because on either side of that y value or x value, the points are below it. So this would be a local maximum. Over here, a function has a local minimum at a point x equals c if nearby f of x is the smallest y value. So here, again, if I drew a little neighborhood around here, we'd say this point right here would be a local minimum because everything on either side of it are above it.
Let's see if we can find a relationship between increasing, decreasing, and local minimums and local maximums by looking at the derivative of a function. So you'll see here in this applet, I have the graph that we just saw when we were defining those terms, and I have a little turtle. So turtle's going to start at A, and he's going to end at B. So here's our function, and what I'm going to do is I'm going to show you the derivative function. So here's the derivative function of this, and I'm going to talk about it as this turtle is going through. I'm also going to show some points and segments. So actually, I'm going to wait to do that. We'll do that after. Okay, so let's just look at increasing and decreasing. So we said before this graph is increasing from here up to here. And then again, from here up to here. So let's see what happens with that first derivative graph, what we notice. So let's have that turtle start. So you can see the turtle, that's that slope of the tangent line. So we can see that he's creating that first derivative value. So here, if you look, that first derivative as he went from here up to here, no matter what, that line was always positive. It was always increasing, so it was a positive slope, but it was starting to slowly decrease how fast it was going up. So the derivative is going down. So we would say that rate of change is positive because we have a positive slope, but that slope of the tangents are getting smaller and smaller as that turtle is getting closer and closer to where I start decreasing. So you can see that slope of the tangent gets smaller and smaller. So notice on the derivative graph, the first derivative function is positive. Okay, this is the green part that the turtle just did, these x values are the green ones. So we had that increasing is on that interval. And notice that our first derivative is always positive, which makes sense. As a function is increasing, if we were to graph the slope of the tangent line there, the slope of the tangent line would always be positive. Okay, but you can see that this derivative is going down because even though the slope is still positive of the derivatives, that slope is decreasing. The rate of change as how fast this graph is going up is going down. So I'm going to say that one more time. The rate of change that this function is increasing is slowing down. Again, you can see here it's increasing fast, and then it starts to increase slower and slower and slower until I hit this value. And at this point, I'm at a local maximum. Now, notice the slope of that tangent line at that local maximum. It's 0. Notice the first derivative graph. It's 0. Let's look at what happens when here we can see this function is decreasing up to here. So let's see what happens to the first derivative graph. And I needed to actually hit the turtle, not the start button, so you get to see this part again. All right, let's hit this turtle graph. So notice it goes down real fast and then it's starting to slow down again. So we can see here the slope of that tangent line as it went from here down to here is negative. And look at the first derivative. It's negative there. The y values are negative. Okay, so again, the first derivative is the slope of the tangent at each x value. So here we can see that those tangents would be negative. We can see they're going to start out a smaller negative because it's not decreasing that fast. And then all of a sudden it starts decreasing super fast in the negative direction, and then it slows back down again until it hits 0. So you can see that part here in that first derivative graph. So it's showing that the graph is decreasing because it has a negative slope, but it starts decreasing slowly and then quicker and quicker. And this is when it's the fastest decreasing, which you can see in this graph right here. And then it starts to decrease slower again. Now here's a local maximum or minimum. And we can see here with this local minimum, the slope of the tangent line is also 0. So we can conclude, and I've got those lines right here where those local mins and maxes are. I've called those M and N. So where a function has a local maximum or minimum, the derivative is always 0. And again, because if you were to draw that slope of the tangent line there, it would be a horizontal line which has a slope of 0. Let's check again what happens here as this function is increasing. So let's think about it. So increasing, if I were to draw the slopes of these tangents, they would be positive. So that means the first derivative better have a y value that's positive, which we can see here. These y values are all positive y values. And we can see this starts going slowly. So these are going to be smaller positive numbers, and then they're going to get bigger and bigger and bigger. And we can see here, this derivative graph starts out small positive, and then it's getting bigger and bigger. And again, we're talking about that rate of change, and that's why that happens. Oops, and I didn't hit start again, but it's okay. This way we can just see it one more time what's happening. So we are going up, and then the turtle goes down, and you can see our derivative graph is negative when the graph is decreasing. And then when this turtle, the graph is increasing again and the turtle's moving up, you can see that that first derivative graph is also positive again. So let's summarize this on the next slide.
Okay, so let's summarize this. The graph of f of x is increasing on an interval AB. If that's the case, then the first derivative is positive, so it's going to be greater than 0. If the graph of f of x is decreasing on an interval, then the first derivative is negative. And where we have a local maximum or minimum, again, we saw when that turtle was there, it had that slope of the tangent line, and that is a horizontal line, which means it is 0. So f of the first derivative of x equals 0 at those minimums and maximum values. All right, let's look at this in an example form. So given the graph of the derivative f prime of x, determine the intervals on which f of x is increasing or decreasing. At what values of x does f have a local maximum or minimum? Okay, so let's first look at increasing. So we just said that a function is increasing if its first derivative is positive. Okay, so here we can see the first derivative. So positive means these y values are positive. So they're greater than 0. So the y values are greater than 0 here. They're greater than 0 here. And they're greater than 0 here. So I would say that this function is increasing. Let's just label these. So it's going to be increasing from negative infinity to -1. And then again from 0 to 1. And then again from 2 to infinity. For decreasing, so we can see this function is decreasing, and that happens when your first derivative is negative. So those y values are negative, those output values are negative here between -1 and 0. And then they're negative again here between 1 and 2. And then we said that a function has a maximum, a local maximum or minimum anywhere we've got the derivative equals 0. Okay, so the derivative equals 0 at all of those x values. So we need to figure out, am I going to be a maximum or a minimum there? So let's write these out. So we've got local maximum and local minimums. Okay, so looking at this x equals -1, let's figure out if that's a maximum or minimum. So we can see here I go from the function is increasing, so that means our original function is going up, and then it goes to decreasing, so that means our original function is going to start going down. So that is a local maximum. So there's a local maximum at x equals -1. All right, let's look at what happens when x equals 0. So when x equals 0, my graph goes from decreasing, so that means my function is going down, to increasing. So that's where the function starts going up. So this function is going to have a local minimum there. So at x equals 0. So when it changes from increasing to decreasing, like right here, that's where you have a local max. And then when it changes from decreasing to increasing, that's where you have a local min. So we would say that there's another local maximum at x equals 1, and then there's a local minimum at x equals 2. All right, let's do this again. Given the graph of the derivative, determine the intervals on which f of x is increasing or decreasing. At what values of x does f have a local maximum or local minimum? Okay, so again here we say that a function is increasing where the first derivative is positive. So that first derivative, I should do this in blue to stay consistent. So that first derivative is positive on this interval, and it's positive on this interval. So we would say that this function is increasing from -infinity to -1, and then from 1 to infinity. Decreasing, so a function is decreasing where the first derivative is negative. So the first derivative is negative all in here, because if this is 0, here's your positive values, here's your negative. So that's going to be negative, that interval is from -1 to 1. Where does it have a local max and a local min? Let's see. So again, where we go from increasing to decreasing, like right here, that's where we have a local maximum, because it goes from going up to all of a sudden going down the original function. So that's going to be a local maximum at x equals -1. And then we'll have a local minimum as we go from decreasing to increasing. So that's at x equals 1.